Hello, I'm Aditya Anugu, and this is my constant velocity Newton's second law lab. To start off, the problem we're trying to assess is that we want to determine how accurate predictive models are relative to experimental results when we're simulating constant velocities of objects in motion. We're interested in this because this experiment allows us to determine how certain assumptions we make while creating simulated models of constant velocities do not reflect how constant velocities work in the real world necessarily. When we do this, we're able to account for errors that might happen in the real world and understand why there are inconsistencies between our real-world constant velocities versus our calculations. Getting into it, we looked at certain assumptions we make in the previous slide when we're creating these simulations for constant velocities. We make these assumptions based on Newton's second law, the momentum principle, which basically states final velocity is equal to initial velocity plus the sum of all forces divided by mass times time. When we say that an object has a constant velocity, we make the assumption that there's a sum of 0 newtons acting on the object total. So the initial velocity will equal the final velocity, hence there will be no change in velocity. Similarly, we can do something similar to position. We can say that final position is going to equal initial position plus velocity times time. Here we can say that for there to be a change in displacement or position, that an object must move at a constant velocity. So in this experiment, we made the assumptions that there would be no change in velocity, no net external force acting on our Rubik's Cube as it moves across an active treadmill. And this treadmill is moving at 1 miles per hour, which is roughly equal to 0.45 meters per second. We assumed there would be no net force acting on the Rubik's Cube because gravitational and normal forces would cancel out, considering that they would be equal in magnitude but opposite in direction. And we know this because there's no acceleration on the y-axis. Similarly, we knew that the cube was not accelerating, so there were no applied forces or frictional forces acting on the cube, at least in the x direction. We know on the x-axis, sorry. We know the cube still moves at a constant velocity because there's a force applied on it at one point when the treadmill was turned off. However, it must have accelerated from 0 meters per second to the constant 0.45 meters per second at some point. But we're not interested in that time period in this case. Rather, we're simply analyzing its constant velocity well after this force has been applied. And we know that there is no need for any forces to be present on an object for it to remain in motion. Hence, we can say that the cube moves at a constant velocity. Here are the experiment references. You may pause if you want to look at them. But I will now move to Tracker. So here is our video. The cube, you can see, moves across the treadmill on this x-axis, and we established that the positive direction on the x-axis would be from right to left. Hence, as time increases, position would increase. And here is the table from which I extracted the time and x position and went into Excel and plotted a graph along with the predicted model. I was able to derive this predicted model from using GlowScript. I used GlowScript in order to graph what a constant velocity would, what the constant velocity from the data would look like. And you can see that the velocity remains constant and its y-intercept would be the initial place it started off on the treadmill. And the slope would be the same slope retrieved from the trend line from the data from Tracker. Then I used the position data from this section, and I was able to plot them together in Excel. Here are the experimental results plotted side by side. As you can see, the datasets vary slightly. However, you can tell that they are very accurate for the most part. However, this inconsistency could be accounted towards the tracker data being skewed, perhaps due to the video being blurry and making it difficult to determine the center of mass in each frame. However, using a treadmill allowed us to get a pretty safe result in terms of getting a constant velocity. As we analyze our data, there's a few important questions we should consider. What if the axes were switched? The graph would appear to be going downward at a constant slope rather than upward because I determined the positive x direction to be from right to left, and plotting the y-axis as the negative x would make it appear as if the object is moving in the opposite direction compared to the original. Hence, it would look like it would be going in the negative direction if the axes were switched. What does the data mean? Like I discussed earlier, the predictive model is very accurate and does not skew much from the experimental data when I assumed the net force was 0 on the object. It is possible to state how many forces are acting on it, considering that the only possible forces in this scenario would have been gravity and the normal forces on the y-axis. However, on the x-axis there are no forces to sum up to 0, as no forces are required for an object to remain in motion. Thank you for watching the video.